It's time to start talking about exponential functions, which are almost certainly the type of functions that are the most useful and applicable in the real world. And you'll see why with some of the questions later on. But the short version is that a lot of things in the world actually do act exponentially, everything from interest and investments to uh, growth and decay and almost everything in nature and pretty much everything else too. And so in this unit, you'll see a lot of real world examples and real world applicable questions that hopefully will make this material pretty interesting. But let's just start by talking about what an exponential function is by comparing it to a linear function. So we know a linear function basically means you're adding the same thing every time. So if we take this really basic example of a linear function, we know if we graphed it, this would have a slope of 3. What that really means is as we move up from like x equals 1 to x equals 2, or from 2 to 3, we're just adding 3 every time. So I'll just kind of put out the first few values here. So if x is 1, y is 3. If x is 2, y is 6, and so on. And so we can see what's happening is basically we're adding the same amount every time. We're adding 3 each time we go up by an integer. So let's compare that to what happens with an exponential function. All right, y equals 3 to the x. So 3 to the first power is 3. 3 to the x, so now x equals 2. 3 to the second power is 9. 3 to the third power is 27. Okay, when x equals 4, 3 to the fourth power is 81. When x equals 5, 3 to the fifth power is 243. So this makes it fairly clear to see what's going on here, that we're not adding the same thing every time, we're multiplying by the same thing every time. And so the difference here is that exponential growth can really accelerate over time. Linear growth does not. It goes up by the same amount every time. Exponential growth does not. You can see that as we keep going here, you could sort of say, okay, this is a difference of 6, and now a difference of 18, and now a difference of 54. And so we're growing, well, what we would say exponentially. This is what people mean when they talk about things growing exponentially, is that the rate of growth seems to increase and increase and increase. And so that's kind of just a basic look at what an exponential function is. It's something that more or less looks like that. We'll look at the form a little bit more in a minute. And the fact, most importantly, most fundamentally, that it grows by you're multiplying by the same thing every time. One thing we'll see, it doesn't always grow. If you have y equals like 2/3 to the x and you're multiplying by 2/3 every time, then it's shrinking each time. So that would be exponential decay. So we'll get to that. And in fact, here's an example right here that if we have a linear function y equals 1/2 x, that these would be our first few numbers. I could put 2.5, but I'll leave it there. If we have, so you notice this number is less than 1. And that's what's going on here is if you multiply by something greater than 1, the thing will get bigger. If you multiply by something less than 1, the thing will get smaller. And so if we're multiplying a half times a half times a half times a half, of course, it's going to shrink each time. So 1/2 to the first power is 1. 1/2 to the second power, pardon me, I said it was 1, it's 1/2. 1/2 to the second power is a fourth. 1/2 to the third power, so that's like 1 to the third over 2 to the third. And so this is now getting smaller and smaller and smaller. Same idea, of course, we're multiplying by the same thing every time instead of adding or subtracting the same thing every time. But it looks a little different. So we have, as I mentioned, words for these. We've got, and I'll include them here. On this first page, this is what we would call exponential growth, because it's getting bigger and bigger and bigger every time, and the rate at which it's growing is also getting bigger. And then what we have here, we would call exponential decay. And this means that something is getting smaller and smaller and smaller over time because we're multiplying by something less than 1. And notice here that the rate of decay actually decreases. Like it goes down by a quarter here. The next time it only goes down by an eighth. The next time it only goes down by a 16th, et cetera. So anyway, that's exponential growth and decay. So let's get into some actual questions with these. And to do the questions, we need our basic exponential form. And here's the basic form that we're going to use. So exponential equations mean that the x value or whatever our variable is in the exponent. Basically, in this format, you're going to have this a value. This is always our starting point. When we talk about questions with investments, this is always going to be the principal, the amount that you invest. If we talk about, and I'll just preview one of the questions on the next page, a scientist visits an island and observes that it has 1,000 birds. Well, if that's our starting point, then this is going to be 1,000. So whatever the starting point is, that's what A is. You can also note that so in exponential questions, almost always this is going to represent time because things are growing over time. So when this is 0, I'll just write this over here. When x equals 0, in other words, at time 0, right when we start, well, anything to the 0 power is 1. So b to the 0 power is 1. So basically that is just 1 times a and it goes away. So what this is saying is that at time equals 0, that's what we have. We start at a. So this value is always going to be a starting point. The b here, and remember, by the way, we don't need parentheses, but only the b is being, let me say that better. The exponent only applies to this b term. It doesn't apply to the a. So that's the starting point. And then this b value is our multiplier. That's going to indicate our growth rate or decay rate. And so in these questions that we did here, we didn't have a starting point really. This was b. In this case, it was less than 1, so the thing got smaller. This was b. In this case, it was greater than 1, so the thing got bigger over time. And so that's exponential form. We have like the amount that we have at whatever point in time is the starting point times whatever the multiplier is, like whatever happens each year, and then to the power of however many years that it happened. So just to give an example with this, like if you have a town has a population of 500 people, okay, so that's its population right at the beginning. And let's say it doubles every year. So after 1 year, after 2 years, after 3 years, after 4 years, etc. Pardon me, that's supposed to be 2. So that would be after 4 years. So in other words, what we're saying is we're starting at 500 and we're just multiplying by 2, like 1 time for every year. So if it's 4 years, we multiply by 2 4 times. That's what exponential form is. So let's apply that to some questions now. All right, the one we looked at a minute ago. A scientist visits an island and observes that it has 1,000 birds. If the population increases 5% per year, how many birds does it have 5 years later? Okay, so let's use, and I'll just jot it off to the side here. Here's our basic exponential form. So we know our starting point. We start with 1,000 birds. When we talk about growth or decay rates or multipliers, we are always assuming that everything starts at 100%. Another way to think of that is if this population never changed, we would just multiply by 1 as many times as we wanted. And we know that the number 1 equals 100%. Just in case this isn't review, or maybe it is anyway, percent literally means divided by 100. That root word cent, like century, centennial, centipede, that means 100. Percent means divided by 100. That's percent. So 100% is 100 per divided by 100. That's why 100% is 1, because it literally means 100 divided by 100. So everything starts at 100%. If something is growing, then that means the next year it's more than 100% of what it was. If something is shrinking or decaying, then the next year it's less than 100% of what it was. But everything starts at 100%. Oh, I didn't mean to delete the whole thing there. Everything starts at 100%. Apparently, I have no choice except to delete the whole thing. Well, that's a bummer. So when this says that the population increases by 5% per year, and you can always come back to this point in the video if you need to, but apparently I can't get away from that. All right. If we say that something increases 5% per year, okay, there's our starting point. That means it starts at 100%, it goes up by 5%. So we're talking about 105%. And as a decimal, we know as a shortcut, we can kind of move the decimal point over twice. That means 1.05. That's our multiplier. That's our growth rate, however we want to look at it. And this is going to go on for 5 years. And just to save us a little math, this is what we'd end up with. Pardon me. For these real world questions, pardon me, I'm still recording this one, a little under the weather. If they're asking about things like people or birds, we're going to round to the nearest whole person or whole birds. We're not going to say, 74.3 people or 1,276.7 birds. We're going to round to the nearest whole number. If we're talking about money, we're going to round to the nearest cent because that's the closest thing we can round money to. But so here's just an opening example of how we can use exponential form. So let's do another one. At that point, so we're starting from 1,276 birds. We're now considering that our starting point. Population starts to decrease by 10% per year. How many birds remain after another 3 years? Okay. Everything starts at 100%. So if it decreases by 10% per year, then our multiplier is 0.90, like 90%. This is just 100%. Everything starts at 100% because of what we had earlier up here, that 100% means 1, which would tell us there's no change. And 100 minus 10%, so 10% decrease, that's where the minus 10% is coming from. That means 90%. And this is going to happen for 3 years. And again, just to save us some calculating, I already have that answer. It would be 930 birds. By the way, if this were all one question, you could actually set this up all at once. Like there's 1,000 birds. The population went up by 5% per year for 5 years, and then down by 10% per year for 3 years. If that were all one question, you could set that all up as one calculation. But let's move on to a couple more examples here. Eldrick runs a dentist's office whose client base has been growing by 8% per year. He currently has 500 patients. If his growth rate stays the same, how many clients will he have in 5 years? So similar to the previous one, just a little more practice. His starting point is 500. His growth rate is 8%, so 100% plus 8%. So that means that next year, this is another way to look at it, next year he will have 100% of what he had. He'll have all of his current people plus another 8%. So that's 108%, which as a decimal, we'll put 1.08. And 5 years, so we're going to multiply by that 5 times. And he'll have 735, again, rounding to the nearest person, patients at that point. Okay, this one's a little different. How many clients did he have 4 years ago? Well, if an exponent of 5 says that we're going forward 5 years or doing this 5 times into the future, then we can set this up the same way and say, well, I don't want to go forward 5 years with a positive number. I want to go backwards 4 years. So a negative number. This is basically saying, okay, we're at 500 now, but we want to undo that 8% increase 4 times to get back to where we would have been 4 years ago. So this is a neat way that you can sort of go forward or backward in time, either way, using positive or negative exponents. I'll show you just so you can see it, one other way that you can set up this question. You could say that, well, the result of getting 500 clients came from, well, we don't know what his starting point was 4 years ago, but from that starting point 4 years ago, he had an 8% increase 4 times. And the math is going to be exactly the same. What's going to happen is we're going to divide both sides by 1.08 to the fourth. So we get x equals 500. So if we remember our exponent rules, 1.08 to the positive 4 in the denominator is the same as 1.08 to the negative 4 in the numerator. So of course it works out the same. They both work. And one thing that this shows you is just a general thing with exponents and exponential equations, I should say, is that you define what your starting point is. Like, I just got the right answer to this question by saying 500 is my starting point and I'm going back in time 4 years, or 500 is my current point, X is my starting point, and then I'm going forward in time 4 years. So as long as you are kind of clear on how you're defining what your starting point is and then writing everything appropriately relative to that, you're in good shape. I just think that using this negative exponent to go back in time is kind of a neat little trick. All right, so let's get to one of the places where exponential growth, and hopefully it's growth if we're talking about money and interest, but this is one of the places where exponential growth or decay is a big deal, is in calculating interest and investment valuation and all that sort of thing. So we do need to start by talking about simple interest, which is not how things usually work. But just to define it, simple interest is that each year or whatever the period is, the bank pays you based on the amount of money you invested in the account. So in this case, let's just read through this question. Earl puts $800 into his bank, which pays 1.2% simple interest on savings accounts. How much is in his account after 3 years? So simple interest means the first year they pay him 1.2% on that 800. The second year, they pay him another 1.2% on that same 800. Third year, they pay him another 1.2% on that same 800. And here's the formula. This is basically saying that after however many years, he's got his original principal, whatever he put in, plus, like, you know, if it's for 3 years, he's got 3 years of that rate on that amount of money. So let's just do the calculation. We'll see what we get. So by the way, the letters change slightly if we're talking specifically about interest and those sorts of calculations. But and by the way, notice this is not exponential. I guess that should have been the headline. Simple interest is not exponential. It's actually linear. We just kind of have to include this because we're going to be talking about more, sorry, bad pun here, more interesting topics in a minute. Let me just do the calculation. Okay, A equals principal. So principal, if we need this definition, that's just the amount that you invest in something, times 1 plus the rate. Okay, let's be careful here. 1.2%. Okay, but as a decimal, move this over twice. So that's 0.012. And you get that 3 times. And again, I've done the calculation in advance. That would give us $828.80. Okay, let's move forward to the good stuff here. Compound interest. Because simple interest is not actually how things work. We said in that last example, simple interest means the first year he gets 1.2% of the 800, and the next year he gets 1.2% of that 800. That's not how it works. The way that these things work is that, okay, let's say, and I'll just use some easy numbers here. Let's say you invest $800 and you get 1% interest. So the first year you get $8, yay. Well, now you have $808 in your account. And so if you get 1% interest on that the next year, well, now you have $8.08 in interest. And then the next year, so you now have $816.08. And so the next year, you get paid interest on that amount, not just your principal, but the interest that got put back into the account, and then the interest you earn on that new amount, and so on. And so then the next year you'd get, if it's 1% again, you'd get $8.16 in interest. And so this is what we mean by compounding, is you're not just getting interest on the original amount, but also on the interest that gets added to the account over time. And so it makes sense this would be a slightly more complex formula, and also that this is the exponential part. All right, what is this formula saying? We're adding one variable here, which is n. And we're going to do a few examples of this. So we still have principal. We still have, okay, a little different in here. One, this is like the 100% of your money that you're still going to have. And what you're also going to have is not just 100% of your money, but also the little bit that you get based on the interest rate. Now, let's say that on this question, we have that same 1.2% interest rate. Let's just start with yearly, and then we'll come back and look at some of this other stuff. All right, so the yearly calculation, A equals principal's 800, 1 plus our rate, again, we kind of figure out how to write it, is 0.012. And so that 1.2% interest is going to happen 3 times. And that ends up being 829.15. Remember when we did simple interest, we got 828.80. So this makes sense that if you also earn interest, like we said here, on not just the principal, but also this amount that got put in and this amount that got put in, yeah, of course, you're going to end up with a little bit more money. Okay. Let's say now, so this is what actually happens basically with interest in bank accounts, is that it gets compounded monthly. What I mean by compounding is that each month they calculate how much interest you earn that month, put it into your account. And so then starting that very next month, you're earning interest not just on your principal, but also on that amount that they've just put into your account. So that's where the compounding part comes from. We're saying like this $8 gets put into your account, not just at the end of the year, but like at the end of every month, they do that. Okay. And also to be clear here, when we talk about interest rates, like here, this says 1.2% interest, just basically without exception, we're talking about annual rates. Okay, so here's how this works. All right, A equals, we're still starting with our $800. I really shouldn't put the dollar sign in the equation like I did in that first one. Okay, what's happening here now is we're not getting all of this once a year. We're getting a 12th of that 12 times a year. So we're not getting all of that 0.012. We're getting 1/12 of that, but 12 times as often. So that's what this whole setup means. So n is the number of times that interest is calculated each year. So if it's calculated 12 times a year, we're getting a 12th of the interest rate, or a 12th as much interest, but 12 times as often. And it would make sense if you're calculating interest more often, so more frequently you're getting that little bit of extra money added to your account, then you should over time end up with a little bit more money. Now, we're using some pretty low numbers here, so it's not a ton more money, but it's more, right? Let's do a couple more of these just to practice with this format. So quarterly, I think that means 4 times a year. So you're getting 1/4 of the interest, but 4 times as often. Well, we'd predict that that should be somewhere between the amount you make if it's compounded monthly and the amount you'd make if it was compounded just yearly. And it is. Oh, I'm sorry. So this is actually, I was looking at the wrong thing on my piece of paper. This was actually 31 cents. And then this is the 28 cents. And then if we were to do it daily, so that would be 1/365th of the interest, but 365 times as often. How much extra would that give us? Well, as it turns out, not a lot. So if you look at these numbers, and this is obviously a random set of dollar values to be using, you can see that, okay, there's a difference between calculating like yearly and monthly, even quarterly and monthly. But at some point, you know, if you say, oh, I want it weekly or I want it daily, it just doesn't make that much difference. That's pretty much why interest in the real world in banks is calculated monthly. To calculate it, you know, weekly or daily would use so much more computing power back in the day, so much more paper and so much more energy, and but it wouldn't really make much of a difference to the bottom line. So that's kind of an intro to exponential growth and decay. And then one of the main ways that it shows up in the real world, which is talking about interest. And there's lots of other ways. But what we want to know from this, just going back to the beginning, is we want to understand what an exponential function is. It's describing a situation where you keep multiplying by the same thing time after time. We want to know what we mean by exponential growth and exponential decay. In both cases, that we're multiplying or dividing by something time after time after time, and that the rate of change is not constant. We're not increasing or decreasing by the same amount with each successive change. We want to know this very general exponential form, which applies to a lot of cases, most cases really. We want to know that A here represents a starting point and B represents a multiplier, or like we just saw in those interest questions, it represents a rate of growth, a rate of decay. How to use that in some standard types of questions that we get with exponential growth and decay. This neat little trick that we can use negative exponents to sort of backtrack in time, not just the positive exponents to go forward in time. And we want to know a lot about interest. Simple interest, we need to know it. It's linear. It's not really how things work, but we should know what it is. And then the big one is understanding how to calculate compound interest, and what this format and all the different variables mean. That's it for this intro to exponential growth and decay, but there's so many applications of it, and so many ways that it's meaningful to understand. But this is the